Hi, in this video I'm going to give a very brief overview of how to check and improve the performance of a Go program. So I'm going to run through certain steps and certain commands and show what these commands or steps show us, which will help us in improving the performance of a Go program. And I won't be going into too much depth of these commands, and I can cover in more details in later videos. So once you have written a Go program, the first thing you should ask is, does this program build at all? Okay, which means does it actually compile? Does the machine can actually understand the code you have written? Because if there's a compilation error, then there is no chance of the program running successfully, right? So the first thing to check is go build, and here the dot stands for the current directory. So you should run go build command as much as you can to first check if there is any syntax error or if the program actually runs at all or not. Okay, so that is the first step. The next thing is, right now you know it runs, so it gives some output. Next thing is to check if the Go program gives the correct output. Okay, so for that we write tests. So tests can look something like this, where here abs is one of your functions and you're writing a test for it, and inside the test you actually call that function and you check its output, whether the function gave the required output or not. So that's the concept of the test. I can explain more about it in a later video. So the command is go test followed by dot or whichever package you want to run a test on. So that shows you if your program can actually give the correct output or not. Okay, so by this time, after doing this build and test commands, you know that you have a solid program which does what it is supposed to do. Next, and only after that, you should check if it is performant enough or not. So some obvious questions to ask would be, how fast does it run and how much memory does it allocate? For that, one of the most basic things one can do is to do benchmark. So here I'm going to go a little bit more into detail. So benchmark in Go, I'm going to show you an example. So here, let's say you have a package called play in play.go, and I have a function here which is called myfunc here. And as you can see, there's an interface, there is a struct which implements that interface, and I have a couple of other functions here. So those two functions f2 and f1 are getting called. One of them has the pointer in its argument, another does not have a pointer in its argument. That's the only difference here. And why I have chosen this example is because when you pass pointers around, then this data gets stored in the heap as opposed to stack. So if there is pointers getting passed around among functions, then that memory is basically shared between these two functions. So that means the common data is stored in heap as opposed to stack, and heap makes it a bit slower compared to stack. So this is something I just explained, but what would you do if you're not aware of this fact? So in those situations, what I'm going to explain from now on might be helpful. So benchmark is one of them. So you write a benchmark of a function in the following manner. So let's say I call it benchmark play, function benchmark play, which takes argument as b, which is of the type testing.b. And here I'm calling this function which I want to benchmark, this myfunc, which I showed before. So that is getting called for certain b.n number of times, and that gets decided by the Go program. And after getting called this many times, we end up seeing certain results like this, where we see how much time per operation takes. So in this case, 35.8 nanosecond per operation, and how much memory allocation, which is heap allocation, is occurring. So it's 2 allocation per operation. Okay, so these are the certain obvious metrics which we can get after running benchmark. And the command for running benchmark is very similar to the command for running test. So we do go test, and we decide not to run any test. Instead, we just run benchmark. So minus b dot then bench mem. So bench mem will show us memory allocations here, and it also shows how much time per operation takes to call this function. So by this time we know how much time it takes and how much memory allocation. Can we know a bit more details about what exactly goes on when a function gets called or when your program actually runs? And there are three other things one can do to check and improve performance of a Go program. So they fall under three aspects. So One is heap allocation, which benchmark shows a little bit but may not give the completely full picture. And then there is throughput aspect and there is latency aspect. So each of them have their own corresponding analysis. So heap allocation you can check by doing something called escape analysis. So I'm not going to too much details, but I will just show you what's the command and what it shows to you, which will be useful. So I already showed you go build command before, right? So if you run go build followed by this flag, so gc flag is equal to -m, followed by your file name, whatever is your package here. So in this case, my package is this play. So if I run that command where this file name would be play.go, then I see output like this, where what you're seeing is basically there are certain inlinings happening where instead of defining a function somewhere else, you might as well just put its corresponding code into where it is getting called. So that is sort of the concept of inlining, which is not really important for us. What is important for us is to see here this %vv literal escapes to heap. As I mentioned to you before, that because we are sharing pointers between two functions, that means that pointer, they have a shared memory between these two functions, and that is stored in the heap as opposed to stack, and that we are literally reading it here, right? So if I see this and if I think, oh, my function is very slow, what should I do? Okay, I have this extra information that, okay, something is getting allocated to heap. So then I can ask myself question whether I can do something to avoid it. Do I really need to pass the pointer or just a value so that it will simply create a copy of it and pass it to the other function so that both the values are stored in the stack and we don't need to utilize the heap, which might make things slower. Okay, so this was escape analysis, which we see the mostly the heap allocation. Next will come CPU profiling, which shows us more information about throughput. So you do CPU profiling after you have written a benchmark. So the corresponding command is the following. So you do go test and then followed by CPU profile cpu.prof, which is the name of the prof file, and you give this bench argument followed by dot if you are in the current directory. And what this does is this creates a file named cpu.prof, and the next step is to visualize that file, which you can do by doing go tool pprof cpu.prof, and then it opens a terminal, and if you enter PDF, then you'll end up seeing something like this. So this basically gives information about what goes on at the CPU level when your function is called. So here, as you can see, because I ran it on a benchmark, that's why we're starting from the benchmark where it calls our function, and here you can see my func, and this is the serial of execution. And inside my func, we see a majority of the time is taken by this function, which is runtime malloc gc, which is basically the garbage collector, which is responsible for collecting the garbage memory from the heap. So that is taking up the most of the effort here, as you can see, which was sort of expected. And there are plenty of other internal functions which may or may not be important. So imagine if you have a very large complicated program, then you may end up seeing certain functional calls which you wrote, which might appear in large boxes. That means you will get to know which exact functions are making your program slow, and then you can go and check those functions and figure out ways to make things faster. So that is CPU profiling, which gives more information about the throughput. And now comes using tracer in Go, which gives more information about the latency. Tracer is a tool that gives an idea about the whole timeline of the Go program, not just what is running currently, but also what is waiting to be run or what Go routine or thread is sleeping. So it gives the whole information, which might be a bit too much, but should be used only if the other checks have not helped you much. So the tracer is integrated to the scheduler, which is responsible for deciding which Go routines actually get executed in the CPU and which one have to wait. So that is something which you cannot just guess. You have to run this program to actually truly have a good idea about it. So that's why Tracer can write logs at nanosecond level. So for example, every time the scheduler takes a Go routine out of the CPU, it writes a log for this. So that means the coroutine is no longer getting executed and it is either has finished or waiting to be executed at later part of the program. So to run the tracer, this is the command which is very similar to what we have been having before. So you use this code test trace.out, which will be the output, followed by package name, and here you give the benchmark function name, and after that it has created this file, and you can simply run go to trace.out to see its output, and the output will look like this, which I have opened up here. So here you see a lot of information basically. So you see the go routines. This is the heap. As you can see, it goes up, then goes down, basically getting dark garbage collected and up and down like this. This will look way more irregular for a complicated program. And here you see all the processes. So there are like, yeah, here you can see 4 or 5 processes depending on how much CPU you have, and you will see what exactly all these processes are doing if you click on these boxes. So as you can see, we have some concurrency here. So initially this process 0 is running, then it is not doing anything, and process 1 is doing something at that time, then process 0 is doing again something, then 1, after some time the 2 comes into picture. So this gives a lot of information about how exactly your program is running and how much time is being spent on which part of the program. So this is a very useful tool which can help you in making your program faster, or at least giving you ideas about where exactly the bottlenecks are. Just a comparison between CPU profiling and tracer. So the tracer, as I mentioned before, stores the entire history of all Go routines. So the tracer gives full event context and not just what is happening at the CPU level at a particular time. But sometimes it might be an overkill to keep trying to find the bottleneck, which in the end may not be too important. So coming back to where we started, that you first check if it builds, then if the test runs fine, which means the program does what it is supposed to do, then you need to ask, okay, if it is acceptable or not, or until what point it is acceptable, and you decide your own target, and if you have achieved your target, then that should be good enough, and you can move on to writing more programs rather than going for an overkill of what is already doing fine. So if you really want to make things up to nanosecond level faster, then sure, all these tools might be very useful for you. So I went through all this fairly quickly, but I can make more specific videos on these later on. So feel free to let me know in the comment section if anything is unclear, or if you want me to make those videos at some point. Thanks.